Hey there, and welcome to Chapter 3, Composition of Substances and Solutions. In this chapter, we'll be going over formula mass and the mole, determining empirical and molecular formulas, molarity, and other units for solution concentration that you will see. All right, so first of all, formula mass and the mole. So formula mass of a substance is the sum of the average atomic masses of all of the atoms in the substance's formula. Okay, you might also see this referred to as a molecular mass, and we'll get to the difference of that in a bit. But basically, if it's a formula mass, can be used for any compound. Okay. You can say formula mass for any compound, but usually we use it for ionic compounds. But it can be ionic and covalent. Covalent substances exist as discrete molecules. Ionic substances don't, and I'll have some slides about that in a little while. But because they exist as single discrete units, kind of like what you're seeing right here, okay, that for chloroform CHCl3, because they exist within these discrete molecules, we can also talk about molar masses. And so this is covalent compounds only, okay? And that's molecular mass. And so as you can see here, we have one carbon in the center. So we have one carbon right here in the center. And then we have 3 chlorines, 1, 2, and 3. And we have 1 hydrogen up here. Okay, and so that means that we have 1 carbon at 12.01. In your periodic table, it's actually 12.011. And then hydrogen, we have 1 of those at 1.008. And then chlorine, and again, your periodic table has 5 significant figures, so this will be 35.453. Okay, and so that'll change this a little bit as well. But then we have a molecular mass. And so that means that 1 molecule of chloroform has an average molecular mass. And remember our weighted averages from last chapter, an average molecular mass equal to 119.37, oh, that one doesn't show up here, atomic mass units. Okay, and now here we show another one. It's much larger. We have aspirin at C9H8O4, and they show you how you find for 9 carbons here and 8 hydrogens here and 4 oxygens here, and then we add it all up for our total molecular mass. And again, this is an average of all of them. It's going to change based on which isotopes we have, but this is a good average. And we're never really looking at a single molecule. We're looking at millions and millions and millions, or trillions and trillions and trillions of molecules all at the same time. And in that case, an average is just fine. Okay, ionic. Now let's look at this a little bit more for the formula mass for ionic compounds. Now, ionic compounds do not exist as individual discrete molecules. Instead, they're composed of cations and anions in this interlocking structure. And so we talk about formula mass as its simplest ratio of ions. Okay, so let's take a look at what that might be. So up here, this top one, you can see sodium chloride. And you remember from last chapter that that means that we have Na plus, oh, this is terrible. And once I do that, I can't undo it. Okay, we have Na plus and Cl minus. And so we know that they form just NaCl. And you can see here that 1 sodium plus 1 chlorine. And so then you have your your formula mass of 58.44. But you never have, like, you don't have this unit here like this. This doesn't exist. What you have is here, okay, where you have each one of these and they're interlocking. And this is only a small quantity of what that might look like, this interlocking structure. So, but we only look at the just a single ratio when we're talking about formula mass. If you go on to Chem 2, you will actually learn how to predict what structure you'll have. So you see down in this bottom picture, we have aluminum sulfate. And remember, aluminum sulfate will be Al3 plus and sulfate SO4 2 minus. And that's how you get this Al2 SO4 3. Okay, you're still going to need to be able to find these. You're still not allowed to take the words aluminum sulfate and look them up. That is an absolute no-no for this entire class. You need to be figuring them out. And the reason for that is because it's very important that you know why they have the ratio that they have and how they're created. But you can see here that the interlocking structure for aluminum sulfate is very, very different than the interlocking structure of sodium chloride. And again, if you go on to Chem 2, you're going to learn about how those differ. And here you can see 2 aluminums, 3 sulfurs, and 12 oxygens to come up with the molar mass. So you're saying, okay, well, where do we get these from? Okay, so let's come over here. This is the first time we've had these parentheses. So here we have 2 aluminums. That's easy. But see this SO4 3? SO4 3 means that we have 3 of these units. Okay. And so you can now see, hopefully, but even if you're not looking at that, this 3 here means that you have 3 sulfurs. And if you have an O4, you have 3 O4s, that's 3 times 4 or 12 oxygen units. Okay, and that's where we end up getting these here. Okay, so now let's take a look at the idea of the mole. Many of you have probably already heard of the mole before, maybe in high school science classes or in biology or even in physics. The mole it's just a number, sort of like saying a pair or a dozen. It's just a lot bigger. Okay, so a mole is defined as the amount of substance containing the same number of discrete entities as the number of atoms in a sample of pure carbon-12 weighing exactly 12 grams. And that's a lot. You don't really need to understand that so much. What you do need to notice is here, the number of entities composing a mole has been determined as 6.02214,179 times 10 to the 23rd. And where this number comes from is it's the amount, so we could say times 10 to the 23rd carbon atoms in 12 grams of carbon. Okay, now this is very long and cumbersome. We don't usually need that many significant figures. So what we use instead is 6.022 times 10 to the 23rd. And this one has 4 sig figs. So just keep that in mind. And this is just Avogadro's number. And it's the number of units per mole. So that might be the number of atoms. That might be the number of molecules. That might be the number of formula units in a mole. You could even say that's how many paper clips are in a mole of paper clips, which would bury the earth in paper clips. Okay, so this picture, I just thought this was kind of interesting because it's showing you sort of the ratios. So if you have 1 mole of each of these, so each of these samples contains 1 mole of atoms, or 6.022 times 10 to the 23rd atoms from left to right. Okay, so we have zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. And I don't have one here, but if you were to go over to your sink and look for 12 milliliters, which is about 12 grams of water, sorry, not 12, I'm thinking about two different things here. Let's come over here. Okay, 18 milliliters. I was thinking about carbon. I don't want to do that because that's not. 18 milliliters of water is about 18 grams of water. Okay, so 18 milliliters of water is also about 1 mole, or 6.02 times 10 to the 23rd water molecules. So the molar mass of an element or a compound is the mass in grams of 1 mole of that substance. It's a property expressed in the units of grams per mole. The molar mass of any substance is numerically equivalent to its atomic or formula mass in an atomic mass unit. So a single 12 carbon. Oh, okay. This should read carbon 12, and this one should be carbon 12. The formatting just got lost here. Okay, not this. Okay, carbon 12 atoms. Okay, that 12 out front is the mass number. Carbon 12 atoms. Okay, so a single carbon 12 atom has 12 atomic mass units, and a mole of carbon 12 atoms has a mass of 12 grams. So they're just the same. Okay, so now let's take a look at this. These numbers come from the periodic table. So remember, from chapter 1, you guys need to have a paper copy of this printed. Very important. Okay, so these just come straight off of the periodic table, and these should be the same. 12.011. This one should be 15.999. Sorry about that. And this one should be 35.453, 35.453. And I don't know why textbooks, regardless of the textbook, this isn't just OpenStax, but for some reason textbooks tend to use smaller ones with only 4 significant figures instead of 5. And when I had come into this, I had clearly started fixing this slide and I forgot to continue fixing it. But again, don't use these numbers, use this periodic table with 5 significant figures on it because we want to have that level of accuracy. Okay, now let's take a look here and let's look at the idea of converting from mass to moles. Okay, so it says according to nutritional guidelines, blah, 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 blah. This is one of those problems that has a whole bunch of useless information in it. We don't care about all the words in here for the problem. And so I like using problems like this in an example so that what we can do is we can take a look here and we can say, okay, well, what's really important? Okay, according to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. There we go. What is the estimated average requirement of potassium in moles? So all this is just telling us that we are going from mass of potassium atoms to moles of potassium atoms. And the way we do that is with a dimensional analysis method. Okay, so one thing students really like is the idea that this should be over 1 and this is times. Okay, so that's just another way of writing it. And the way that you would type this into your calculator is 4.7 divided by 39.10. And you can see in this problem that we only have 2 significant figures. So in our answer, we only have 2 significant figures. Okay, so let's take a look at another one. And now in the last problem, we were going from grams to moles. Well, in this problem, we're going to be going from moles to grams. Okay, so it's the same type of problem and we're just looking at it backwards. Okay, so again, here we have a liter of air contains 9.2 moles times 10 to the negative 4th moles of argon. So that's in 1 liter. And here we have, so here's this. And then it says, what is the mass of argon in a liter of the air? And if they don't specify what they want for the mass, you can usually assume that they're looking for it in grams. If they wanted it in milligrams or micrograms or kilograms, then they'd specify that. Okay, so now again, here we have 9.2 times 10, and you can imagine this is over 1. and times. Okay, and so the way you would type this into the calculator is 9.2. Now every calculator is different. Remember that scientific notation can be kind of weird. Your calculator might do a variety of things. It might have an EE button. It might have an EXP button. It might have a times 10 to the X button. And then last but not least, you might need two buttons, usually something like a second comma or something. And these are the most common forms for that. So 9.2 and then one of these sections and then -4. In fact, even my calculator, I have to put the negative in after the 4. Okay, and then times 39.95. And again, here, if we look at this, we have two significant figures here, and we have two significant figures here. Okay. And this right here is the molar mass. Okay. And we get that off of the periodic table. Okay, so now let's take a look at something a little bit more complicated. So here it asks us to convert from mass of a compound to moles of a compound. And as I'm looking at the slide, I'm realizing that it looks a little bit incomplete. Okay, so what they should say here is how, let's see, how many moles of, what do we have here? Glycine are in 28.35 grams. Okay, there we go. Our problem might look a little bit like this. Well, and so here we go. Here is our step 1. Okay, the step 1 for this problem is find your molar mass. And interestingly enough, if you're not sure where to start a problem, just start by finding a molar mass. Chances are you're going to have to do it at some point in time. So you might as well start with that. That'll give you some partial credit, at least on a test, if you're not sure where to go from there. But step 1, if you can't think of anything else to do, start by finding a molar mass. I'd say that 9 times out of 10, you'll need it at some point in time. Okay, and this shows you how to find it. So here is glycine right here. Okay, it has 2 carbons, 5 hydrogens, 2 oxygens, and 1 nitrogen. And as we look in here, you can say, ooh, what's what? And that's a good question. If we look in here, you can see that you have your carbons are here in black. Okay, and your oxygens are here in red. And this one blue atom that we have here is your nitrogen. And your hydrogens are the ones here in white, and that won't show up at all. So we'll do it in blue. Hydrogen, there's 1, 2, 3, 4. And it's not showing the last one. My guess is that the last one is behind this carbon here, and it's just not. I'm trying to see. I can't see it. So this picture it's difficult to see, but my guess is, because we need another one here, is that there's actually probably that you can't see, there's probably a little hydrogen back here as well. Okay. But usually you won't be working off of a picture like this. You'll be working off of a compound, and that compound might tell you that glycine is C2H5O2N. Okay. And that is more commonly how you'll be finding your molar mass. So again, your first step here is find your molar mass. You can put this over 1 if you want to and multiply. And what that means is 28.35 grams. And then you divide that by 75.07. And here you can actually see in this case that you have 1, 2, 3, 4 significant figures. Interesting. They calculated this. This slide comes from something else. They calculated this, and we only have 3 significant figures. And here we have 4 significant figures as well. So let's go ahead and take a look what that would be. That would be 28.35 times 75.07. Okay. divided by, I even said it backwards, wrote it correctly, said it back, 28.35 divided by 75.07. Okay, these both have 4 significant figures. So let's take a look at what we would be doing with that. And this gives us 0.3776477529. Okay, and we see 4 significant figures here. We see 4 significant figures here. That means that we can have 4 significant figures in our final answer. So this should be 0.3776 and moles glycine. And so our answer is moles glycine. And I'm actually going to cross this out. So that's a good example of sometimes you'll find errors even in things. Some of these slides I made, this isn't one of the ones that I created myself. So it's always good to be looking for that, but always consider where your final answer should be. Sometimes I won't take points off if there's too many digits, but if you over round, I will always take points off. So if you need to give me 4 significant figures, but you give me 3, that's called over rounding, and I will always take some points off for that, because what you're doing then is you're actually decreasing the accuracy that you can actually be presenting. All right, now let's look at another one like this. It says vitamin C is a covalent compound with the molecular formula C6H8O6. Okay, and the recommended daily allotment is for children 4 to 8 years is 1.42 times 10 to the -4th moles. So they want to know what is the mass of this allowance in grams, and they actually tell you here. You don't have to find it. Now remember, your first step would usually be to find your molar mass. Okay, so then with this, so when you're going from moles to mass, again, you're just multiplying by that molar mass. And so we'll put this over 1 and times, and it's 1.42 times 10 to the -4th times 176.124 grams. Now in this case, we can see that we have 1, 2, 3 significant figures, and here we have 1, 2, 3 significant figures. Okay, so we're good. What would this actually look like if we were to calculate it? 1.42, and now I put in whatever I use for scientific notation, 10 to the -4th, okay, and multiply that by 176.124. All right, well, what I actually get for this answer here is 0.025009608. It's grams. And then I know that I can have 1, 2, 3 significant figures, because remember, our leading zeros don't count. And that was actually a very easy round, because we just have a 0 following it. So it just becomes 0.250. You have to include that last 0. Remember, if you did not include the last 0 here, then it would only have 2 significant figures, and it's definitely not 2 significant figures. Okay. Now let's look at another example. And I'm just showing you these examples. Again, I really hope that while you're watching this, what you're doing is you're pausing the video and you're writing things down, because chemistry is a science of mathematics, and you can only learn mathematics by doing the math. So please be pausing the video and taking notes on these slides. Okay, so now a packet of an artificial sweetener contains 40 milligrams of saccharin. And here is our chemical formula. And here's our structural formula. And what this is doing now is you don't need to be able to go from this chemical formula to the structural formula at this point. It's just really, really good practice for you to see them and begin learning how to link them. So let's take a look here. It says, given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in 40 milligrams? And it even gives you a conversion here, 0.0400 grams sample of saccharin saccharin, and how many carbon atoms are in that sample. Okay, so let's take a look at what this would be. All right, so first of all, there's a whole bunch of questions in here. And the first one is how many molecules are in this sample? So first, we have to go from mass to moles to molecules. Okay, so we see that we start here with 0.0400 grams times, now we need to get rid of the grams, and so we need grams down here, and we know that we can go from grams to mole, and that's what this conversion is, 183.18 grams per mole, and that allows us to get rid of our grams. Okay, so here you can see that we're dividing by our molar mass in grams. Okay, now we know that the way to go from molecules to moles is with Avogadro's number. And now here we have moles on the top, so we'll need moles on the bottom so that they'll cancel. And it'll be 6.022 times 10 to the 23rd molecules on top. Okay, and that's going to tell us how many molecules we have. And the way I am going to put this into my calculator, so I have a very simple calculator. And that means that I have to kind of hit enter into every one. So one thing that's kind of the easiest way to do this is to multiply everything on the top, ignoring one. So this becomes 0.0400 times 6.022 times 10 to the 23rd. And remember, put it into your calculator correctly. And so the top now becomes 2.4088 times 10 to the 22nd, divided by what we have on the bottom, 183.18. Okay, so I divide that number by 183.18. Okay, and what I get is 1.3149972 times 10 to the 20th. Okay, and I can see here though that, see this right here? This is my known or my given, and in it I have 3 significant figures. So my overall answer here can only have 3 significant figures in it. So we get 1.31 times 10 to the 20th, and that's molecules of saccharin. Now notice here, there's a second piece. It says how many carbon atoms are in the sample. All right. And what I would do with this now is I would say, okay, well, we know that in one molecule of saccharin, there are 7 carbon atoms, see? So you could set this up and you could say 1.31 times 10 to the 20th molecules. And now watch, this is how we know that we're doing it correctly. We know that in one molecule, there are 7 carbon atoms. So we take that 1.31 times 10 to the 20th times 7. Now we've counted that 7 carbon atoms, so that doesn't figure into our significant figures. We can still have 3 significant figures. So the answer here becomes 9.20 times 10 to the 20th carbon atoms. So those are the 2 answers to this piece here. Here's the carbon atoms, and here are the molecules of saccharin. Okay, now what we have here is we have an example. All right, so if you are taking an in-person class with me, I would do one of these and then you would do one of them on your own. So I'm going to show you how to work through one of them, and then on your own, you should work through them. And then if you're taking this as an online class, okay, so if you're taking this class in person with me, when you come to class, we will do the second part of this slide. If you're taking this as an online asynchronous class, then go ahead and work through this, and it will be in the slide answers that I send out to the class. Okay, so let's go ahead and take a look here. Okay, so we have consider the ionic compound aluminum phosphate and the covalent compound methanol. Okay, so the first thing that we're going to do in this setup is we're going to say, okay, first of all, we're always going to need to start with a formula. And we have aluminum phosphate, and that's aluminum ions, Al3 plus, and phosphate ions, PO4 3 minus. Now you can see that the 3 plus and the 3 minus balance each other completely. So we get AlPO4. Now, this is the one I'm going to show you in this slide. And then what I would want you to do is I want you to work on the methanol on your own. Again, if you're seeing me in class, you'll be doing that in class. If you're not seeing me in class, you'll be doing it at home as an online exercise. Okay, so now let's take a look at working through this for aluminum phosphate. The first thing here is it says determine the number of moles and formula units or molecules in a 100-gram sample. Okay, now I mentioned this before and I'll mention it again. The first step, almost any time that we're working on this, is going to be, so we could even call this step 0, but we'll call it step 1, is to find your molar mass. Always, always. Okay, that's like always going to be step 1 here. Okay, so that means that we have one aluminum atom at, there's my periodic table right here. So I have one aluminum atom at 26.982. So we'll say 1 times 26.982. And then we have one phosphorus. And so that's 1 times 30.974. And here we have 4 oxygens. So that's 4 times 15.999. And this is how I want you to show all your work. After chapter 3, you do not have to show all of these pieces, because I know that many people can sort of do it just on their calculator looking at their periodic table. However, in chapter 3, in order for me to know that you're actually doing all of this work and not looking up, in order to get points for these problems, any problem in chapter 3, you have to show me where your molar mass comes from. Okay, if you don't show me where your molar mass comes from, I am going to assume in this chapter that you looked up the answer. Okay, so you have to do this part. Okay, so now let's go ahead and add this all up. Okay, and what I get here for my molar mass for aluminum phosphate is 121.952 grams per mole. Okay, always going to be kind of that step 1 for pretty much every problem. Okay, now it says determine the number of moles and formula units or molecules in a 100-gram sample. Okay, so let's start with the number of moles in our sample. Okay, so we have 100 grams times, now remember we're converting from grams to moles, so we need to cancel out our grams, and grams need to go on the bottom. So 121.952 grams per mole. And that cancels out our grams. And we do this by doing 100 divided by 121.952. And we can have 4 significant figures. So this one gets a little tricky, because what I get on my calculator is 0.81999. And I'll just stop it after the 4. And I can have 1, 2, 3, 4 significant figures. So how do I do that? I mean, this is a 9. That 9 needs to round up. So the way that you're going to report this is 0.8200 moles. Okay, and that is our aluminum phosphate. Okay, so that was our step 1. Now you'll notice here that they also say formula units, and I don't have room right here, so I'm going to come down here and show that. So in order to find formula units, now we can start with that 0.8200 moles times, in 1 mole, you always have 6.022 times 10 to the 23rd units. And I'm just going to use formula units. Formula units is too long to write. Okay. And so this means that now if we have that aluminum phosphate, if you were doing the methanol above, you would be calling them molecules because methanol is covalent. And so those are molecules, but aluminum phosphate is not covalent, it's ionic because it starts with a metal. And so we know where that is. I'm not sure what this times is. There we go. Okay, so we have 0.8200 times 6.022 times 10 to the 23rd. I can have 4 significant figures. And so what I get here is 4.938 times 10 to the 23rd units. So those are ratio units or formula units of aluminum phosphate. Okay, and that was the second part of this first question. Now it says determine the mass and number of formula units or molecules in 5.78 moles of each compound. So in this in the first part, we were going from grams to moles. And in the second part, we're going from moles to grams. Okay. So in the second part, we say, okay, well, we're going to start with 5.78 moles. And as usual, we need to cancel this out. And because we have moles here, we'll need to put moles on the bottom. And in 1 mole, we have 121.952 grams per mole. And we had found that here at the beginning. See, that's why it's so useful. You find it at the beginning and then you've got it for the rest. And that cancels out our moles. So then we have 5.78 times 121.952. And now in this one, see, we can only have 3 significant figures here. So this becomes 700 and, well, first of all, I'll show you my calculus is 704.88256. But with our significant figures, this becomes 705, and we're left with grams of our aluminum phosphate. And the second part asks for formula units for the aluminum phosphate or molecules for the methanol. And with that one, we're actually going to start with the number of moles that we had again. So with this first one, we found moles and then we used the moles to find units. Now we've already got moles. And so we'll do that again. And we can say that in 1 mole, remember, there are 6.022 times 10 to the 23rd units. Again, when you're working on the methanol on your own, that will be in molecules, not units. Okay, so we have 5.78 times 6.022 times 10 to the 23rd using correct, the correct thing for our calculator. Again, we can have 3 significant figures now, and this becomes 3.48 times 10 to the 24th units of aluminum phosphate. Okay. So you'll notice these problems are big. Chapter 3 is a lot of math. So give yourself time, do as much of it as you can. Maybe even watch and pause, but make sure that you're writing down all of the math that I'm doing in these slides. Very important. Okay, now let's take a look at empirical and molecular formulas. Okay, so a percent composition is the percentage by mass of each element in a compound. So there's a couple ways of doing that. First of all, if we have a 10-gram sample of a compound and we see that it has 2.5 grams of hydrogen and 7.5 grams of carbon, then what you have here is the mass of the element over the mass of the compound times 100 gives you the amount. So 2.5 grams of hydrogen, 7.5 grams of carbon becomes 25% hydrogen and 75% carbon. So this is how you would find the percent composition for elements within a sample. Now let's take a look. You can also find percent composition directly from a molecular or an empirical formula. So the way you do that is just by counting everything up. So let's take a look at this. Here we have ammonia, NH3, and it tells you that your formula mass is 17.03 atomic mass units. This is also what you could also call this the molecular mass. Okay, because ammonia exists as a molecule. Okay, so here we say, well, we have one nitrogen at 14.01, and we have 3 hydrogens at 1.008. I'll go ahead and use their numbers. And so what you do is you use that one nitrogen here divided by your total, because when you add all of these up, you get that 17.03. And so it's the mass of the nitrogen in the compound divided by the total. And here you have the mass of the hydrogen in the compound divided by the total. Turn into a percent, and you would say that in ammonia, you have 82.27% nitrogen and 17.76 hydrogen by mass. All right, now we can use those in order to find our empirical formula. So this is a little bit like if you ever watch a crime drama, or someday if you end up working in a crime lab, sometimes you'll be like, they'll be like, oh, look, we have this unknown substance. And then they send it to the nebulous lab somewhere, and the lab tells them what they have. Well, this is the process that the lab is going through. Whenever you have an unknown, one of the simple ways of figuring out what your unknown is, and by unknown is you're in a lab and you have some stuff and you don't know what it is. And that's, what you have there. And one of the simplest ways of figuring out what you have is by using something called a mass spectrometer. And the mass spectrometer will tell you, or it will give you, the percentage of your sample that is each atom. So sometimes we'll know how much of something we have, but we won't know what it is. Excuse me. Okay, so your first step in here is to convert your element masses to moles using molar mass, and we've done that. Your step 2 is going to divide each number of moles by the smallest number of moles, okay? What this will do is that this will give you ratios to work with against 1. All right, and then step 3 is to multiply these by an integer if needed to give the smallest whole number ratio of subscripts. And here you can see the process. Now this is going to make more sense after you see the process. So if you didn't take notes while I was talking, you can watch the process and then come back and do that. Okay, so what do we have? It says a compound is determined. So first of all, there's a couple of different things here. One of these is what you're seeing right now, and that is determining empirical formula from sample mass. So here what we have is we have a compound, we have an unknown, and in this unknown, you can see that we have 1.71 grams of carbon and 0.287 grams of hydrogen. Okay, so in order to find that, we say, okay, well, first of all, let's find, remember our step 1. Our step 1 is to find the moles in our masses. Okay, and you do that by dividing by your molar mass here. So you have grams of carbon and grams of carbon on the bottom. So this is 1.17 divided by 12.01 gives you 0.142 moles of carbon. And then you have 0.287 grams of hydrogen. And so you have grams of hydrogen on the back. Oh, and there is a typo here. This should be moles hydrogen there. Okay, so 0.287 grams of hydrogen divided by 1.008 grams of hydrogen per mole of hydrogen. And actually, you know what I'm going to do? I'm going to we'll erase that, and I'll actually, there we go, hydrogen. Okay, gives you 0.284 moles of hydrogen. Now we need to figure out what this is as a ratio. And so you always identify the smallest one, and that's your carbon here. And so you can see here, carbon is 0.142 and 0.284. And when you set it up like this, and then you divide it, 0.142 divided by 0.142 is 1. and 0.284 divided by 0.142 is equal to 2. And so then you set these up. This would be C1H2, but we never really say C1H2, it's just CH2. Okay, now let's take a look at another example of this. So first of all, it gives us a compound is determined to contain 5.31 grams of chlorine and 8.4 grams of oxygen. Okay, so what I'm going to do is I'm just going to come over to the side here and I'm going to show you how to do this again from the beginning. So first we start with that 5.31 grams of chlorine, times, and chlorine I can see on my periodic table is 35.453 grams per mole. Okay. So then I do 5.31 divided by 35.453, which gives me 0.14 and 977. So if I can only have 3 significant figures here, 0.14977 becomes 150, and that's moles of chlorine. Okay, and then here I have 8.40 grams of oxygen, and 1 mole of oxygen is 15.999 grams. And so I have 8.4 divided by 15.999. And I can have 3 significant figures. And so this one is 0.525 moles of oxygen. And now I can set it up. I have Cl, and I notice that the one for chlorine here is the smallest. So what I'll do is I will say, okay, well, I have Cl and I have decimal point comes first. I have 0.150 over 0.150. And then I have oxygen 0.525 over 0.150. Okay, so the chlorine becomes Cl1. Now let's take a look at the oxygen, 0.525 divided by 0.150. And I get O, 3.5. Okay, well, that doesn't look like a chemical formula at all. So what I would do is I would say, well, 3.5 times 2 is 7. That's how you get a 0.5 to a whole number, is you multiply it by 2. So we're going to multiply each one of these by 2 so that they're whole numbers, and we get Cl2O7. And that would be our empirical formula for this compound. So now the next slide is determining empirical formulas from percent compositions. So this has kind of an extra step in it because it's going to have a percent composition, and that percent composition might be something, something percent. And what you do is you say, well, because it's all about ratios. So I can assume I have 100 grams. So what this means is that if I had 15%, then that means that I would have 15 grams of that element. Oops, I can't, hang on. I would have 15 grams of that element to 100 grams total. Now, if there were only two elements, say, then the next one would be 85 grams. They all have we'll say 15 grams of element 1, 85 grams of element 2. Out of, again, 100 gram total, because everything has to add for that 100. Okay, and then we use the exact process that we used before. Again, we convert element masses to moles, and then we divide each number of moles by the smallest. And if necessary, like we saw in that last example, you multiply by some integer, 2 or 3 usually, to get you a small whole number ratio. Okay, so let's take a look at what that process might be. Here we have the bacterial fermentation of grain to produce ethanol forms a gas, and it's 27.29% carbon and 72.71% oxygen. And they want to know what the empirical formula of this gas is. Okay, excellent. So here we have the 27.29% carbon, and we just change that to 27.29 grams. And then we divide by 12.01 to get 2.27 moles of carbon. And then second here, we have 72.71% oxygen. And what we've done here is we've just converted it, and you can see it up here as well, to 72.71 grams of oxygen divided by, here they've rounded to 4 significant figures, but do 15.999. It won't change things much in these, for 4.544 moles of oxygen. Okay, now again, we take these and you can see where they go here. So here you have that 2.272 for the carbon, and the 4.544 goes here, and that doesn't look right. So you divide both the 4.544 and the 2.272 by the smallest, which is 2.272. And that comes out evenly to give you C1O2, or CO2. So what it's releasing is carbon dioxide. Very, very common, because here we were talking about bacterial fermentation. Basically, anytime you are respirating, whether you're bacteria usually, or humans, or dogs and cats, your respiration releases carbon dioxide. Okay, so now let's take a look at deriving the molecular formula from an empirical formula to a molar formula, or a molecular formula. Okay, and you do that by using molar mass. So for example, here we have an empirical formula, CH2O. Now the empirical formula of CH2O, they're rounding it here to 3 atomic mass units, and I would not want you doing that. Let's take a look here. Okay, so here we have 1 carbon at 12.011, and we have 2 hydrogens at 1.008, and we have 1 oxygen at 15.999. Okay, now this gives you an empirical formula molar mass of 30.026 grams per mole. Okay, now they have to tell you that your molecular mass for this substance is 180 atomic mass units. Okay, and so it really doesn't matter too much here because you're going to be rounding to simple whole numbers. But what they're showing here is it's this molecular mass divided by empirical mass. Okay, and that was what we saw up here. When we divide 180 by 30, we get 6. And so we multiply each one of these, 6 times 1 carbon, 6 times 2 hydrogens, and 6 by 1 oxygen gives you C6H12O6. Okay, next we have solutions. All right, and don't worry, here we're going through these, just one example each, but remember at the end of the PowerPoint slides, there will be a bunch of practice problems. You're watching this at home, whether you're taking it in class or outside of class, because again, we're working this as a flipped class. And so here I'm teaching you the basics. When you come into class, you're going to spend a couple of hours sitting down and practicing this with me. So this will not be your only practice. If you're taking it online, take a look again. You can even have the video running and the problems at the end, in the end slides to work through, as well as the recitation and the reading comprehension homework. Okay. All right, so let's take a look at solutions. A solution is another word for a homogeneous mixture. Do you remember homogeneous mixture from chapter 1? It had uniform composition and properties throughout its entire volume. All right, so the relative amount of a given solution component is known as its concentration. And there's a couple of very important terms. The first one is solvent. The solvent is the component with a concentration that is significantly greater than all of the other components. The solute is the component that is typically present at a much lower concentration than the solvent. And any solution in which water is a solvent is called an aqueous solution. So let's take a look at a couple of examples for what this might be. Okay, so let's imagine here we have a pot of water boiling on the stove, and we want it to boil hotter, not faster. I can explain that to you if you want to, but we have our pot of water boiling on the stove, and we wanted to cook our pasta quickly. And so we want our water temperature to be hotter. And what we're going to do then is we're going to actually want to make all of this look like water. There we go. We want it to go, and so what we're going to do is we're going to add salt to it. Most of you have seen something like this. We're going to add salt to it, and salt, table salt, is just sodium chloride. And so what happens is it's going to come in here and it's going to dissociate, and we're going to have our Na plus and our Cl minus and our Na plus and Cl minus and Na plus and Cl minus. And in this, what we will find is that our solute is our sodium chloride and our solvent is our water. And this is an aqueous solution. Aqueous solution, it means that we are dissolved in water, or water is our solvent. So one of the most common ways that we describe concentration is with molarity. Molarity is the number of moles of solute in exactly 1 liter of solution. And so a lot of times you'll also see this written as molarity equals moles per liter. And molarity, capital M, is a useful concentration unit for many applications in chemistry. This is molarity with a capital M. Little m here means molality, and you won't get to that until Chem 2, okay? But molality is completely different. That's your moles per kilogram solvent. So that's very different. So make sure that when you're talking about molarity, use a capital letter M and not a lowercase m. Okay, so let's take a look at a problem for that. So first of all, it tells us that we have 355 milliliter soft drink, and it contains 0.133 moles of sucrose, which is just table sugar. What is the molar concentration of sucrose in our beverage? Okay, so in this, our step 1 needs to be to convert our volume. Our volume needs to be in liters. Now, sometimes it'll already be in liters, but if it's not, we need to convert it to liters. Okay, so that means that we have 355 milliliters times, we have 1,000 milliliters per liter. Okay, so this becomes 0.355 liters of solution, because you can only do molarity in terms of liters. That has to be, no matter what, kiloliters, microliters, milliliters, centiliters, whatever you're doing, it has to be in liters. You have to convert it to liters first. And now this is already in moles. So we know from before that molarity is equal to moles per liter. Okay, that was from the last slide. Okay, so, and now we want to know the molar concentration. So we say, all right, molarity is equal to our moles, 0.133 moles, divided by our volume in liters, 0.355 liters. Okay, this is handy. They're both 3 significant figures, so we know that that's where we can end. So we get 0.133 divided by 0.355, and we get a molarity of 0.375, and you can actually write molar. That's our unit for that. Okay, now we have, it says, now we're looking at a second problem here. So I'll go ahead and change my ink color. I'll go with it, nice burgundy. What volume of 0.2 molar potassium sulfate, K2SO4 solution contains 57 grams of our K2SO4? So remember, molarity is moles to liter. So our step one for this problem is to find our molar mass. And our step two for this problem will be to find our number of moles. All right, so step one, we have K2SO4. So we have 2 potassium. So that's 2 times, got to grab my periodic table here, 2 times 39.098. And I'll kind of do that. There we go. We have 1 sulfur. So 1 sulfur is 1 times 32.065. And we have 4 oxygens, 4 times 59.999. And so all of these added together I lost it, there we go, is equal to 174.257. And that's grams per mole. And that was our step one. Now our step two is to turn this 57 grams into moles, because that's what we need for our molarity calculations. And we start with grams, so we need grams on the bottom. Okay, so that's 57 divided by 174.257, which equals 0.327 moles. Okay, now we're up to our step three. Now our step three for this is going to be to find our volumes. Now see how it says what volume? So if molarity equals moles divided by liters, the way we would turn that around is that we would then say that liters equal moles divided by molarity. Okay, so we get 0.327 moles divided by 0.20 molar. And now we can see we can have two significant figures in our final answer. We get 0.327 divided by 0.20, and we get 1.635 liters, but we can only have two significant figures in our final answer. So this becomes 1.6 liters for our final answer for this problem. Okay, now our next thing that we're working on here is dilution. So dilution is the process where you're taking the concentration of a solution and you're making the concentration lower by adding solvent. So this is a good kind of example for this. Here we have a concentrated solution. And we take our concentrated solution and we add, it's probably water, but we'll say we add solvent to form a dilute solution. And hopefully you are taking this in class and you're looking in the lab. If not, you're probably watching one of these labs, and you can see how it actually, if you have a solution with some kind of color to it, like copper nitrate, then you can actually see that it gets less concentrated just visually. Okay, so let's take a look at the way that we do that math. We know that, so N sometimes is moles. So remember that we had molarity is equal to moles per liter. Sometimes the term mole is abbreviated as N. And you're going to see that a lot later, especially in gases. So you can say molarity is equal to N over L. But that means that our number of moles, N, is equal to molarity times liters. Okay. Now, when you're diluting something, you're not changing the number of moles. You're only changing the volume, and then by the volume, the concentration. So you can say that the number of moles before dilution is equal to molarity times liters, and the number of moles after dilution is equal to molarity times liters. Well, but then, and this is a really important thing, in dilution, we don't change. So we have N1 equal to N2. So moles before, moles after. But so that means that we can do M1, L1 is equal to M2, L2. Sometimes people will write C1, V1 is equal to C2, V2, where C is concentration. The most common thing actually that I have seen is M1, V1 equal to M2, V2. And one of the reasons that we don't continue using the L's is that as long as you have agreement, your volumes don't have to be in liters because this is a ratio or a proportion. So V can be in milliliters or microliters or liters, as long as they're both in microliters or they're both in milliliters. They just have to have that agreement. Okay, so next we have, I'm just trying to see, okay, we're almost done. I won't break this time. So we have, let's say that we have a problem and in it we have 0.850 liters of a 5 molar solution of copper nitrate. And oh, this is very interesting. This is a kind of a no-no. Again, I didn't write this problem, but look, copper nitrate. But which copper do we have? That might be an important thing to know. So you can see here that we have CuNO3 2. If our nitrate is NO3 minus, that means that our copper is Cu2 plus. And this is important to know because copper 2 and copper 1 behave differently. So you probably should know what you're working with. That means that this actually should be copper 2 nitrate. Okay, and now we're going to dilute it by to a volume of 1.8 liters. Okay, so we went from 0.85 liters. Okay, and it says, what is the molarity of the diluted solution? All right, so let's take a look a little bit at what we got going on here. So our initial concentration is 5 molar, and our initial volume is 0.85 liters. And our final concentration, well, that's the secondary molarity that we're looking for. And our final volume is 1.8 liters. And now you can solve this. See, if you're solving for C2, you do that by dividing both sides by V2, which is how they got this equation here. C2 is equal to C1 V1 over V2. And we put in our values and get 5 times 0.85 divided by 1.8 will get you 2.36 molar. And that's how you find that final concentration. Okay, so now let's look at a couple more. First, we have mass percentage. Okay, and mass percent and percent composition are a little bit different. A mass percent is looking at the mass of a component divided by the mass of the solution. Okay, so when we were talking about percent composition, we were talking about one element out of a compound. When we're talking about mass percentage, we're talking about the mass of a component. So a full molecule or a formula unit divided by the mass of the entire solution times 100%, we'll say. Okay, and then you can do volume percentage, and honestly, I haven't seen volume percentage quite as often as I've seen mass percent, but it can be very useful because sometimes it's easier to, if both your solute and your solvent are liquid, sometimes it's a little bit easier to do volume of solute instead of mass. And again, that's times percent to turn it into a percent. Okay, so let's work through a fairly complicated problem on this. Okay, so it says commercial vinegar is 5.010% acetic acid by mass. How many grams and moles of acetic acid can be found in 100 milliliters of vinegar? Okay, so if they don't give us the density, one of the things that you need to remember is that the density of water or anything aqueous, so the density of water and therefore aqueous solutions is about 1 gram per milliliter. So if we have 100 milliliters of vinegar, if they're not going to tell us the density, you can assume then that that's 100 grams of vinegar. Now, if we have 5.010% acetic acid. Now remember, acetic acid, we have H plus and the acetate ion. So acetic comes from acetate. And the acetate ion is C2H3O2 minus. When we put these together, we have 5.010% H, C2H3O2. And out of 100 grams, that means that we have 5.010 grams of acetic acid, HC2H3O2. That's what that means there. Okay. All right. So now our next, it says, what is the molarity of the solution? So now we have our volume. Okay. So let's come over here and we will remember that molarity is equal to moles divided by liter. And that's what we need next. So we need to turn this into moles and this into liters. So first of all, 100 milliliters, okay, divided by 1,000 milliliters in 1 liter means that we have 0.1000 liters of our solution. So that's our volume. And now we have 5.010 grams of acetic acid. This is where you say, oh, right, the first thing I was always supposed to do was to find my molar mass. Okay, so let's come over here and we'll say, okay, now see how I have 2 carbons? That's 2 times 12.011. And I have 1 hydrogen out front and 3 hydrogens in the middle. So that means 4 times 1.008 and 2 oxygens, 2 times 15.999. And that means that the molar mass of my acetic acid is 60.052 grams per mole. And that's why you might as well find your molar mass, because 9 times out of 10, you're going to need it. Okay, or you can do it later when you realize that you do need it. Okay, so now we have 5.010 grams times, and we have that 60.052 grams on the bottom and liters. So what we're doing is 5.010 divided by 60.052, and that gets us 0.08343 moles. Okay. Here I have 4 significant figures and 4 significant figures and 4 significant figures in my volume as well. Now I can finally finish this problem and say that my molarity is equal to my number of moles, 0.08343 moles, divided by my volume in liters, 0.100 liters. Okay, and now this gets me 0.8343 moles. Oh, sorry, not moles. It was moles per liter. See, that's why I should always write this here, moles per liter, which tells me that that is molar for molarity. All right. 2 more quick slides, and then I promise you're done. Chapter 3, I actually really like the OpenStax. When we used a different textbook, chapter 3 was twice as long as chapter 2 because of the way they broke everything out, and it made chapter 3 really, really long. Okay, our last bit is parts per million and parts per billion. And this can seem a little bit challenging, but if you kind of follow these steps, it's not too terribly bad. Okay, so first of all, ppm, parts per million and parts per billion. Now, and this is often used, especially like by the EPA or some, it's in some places called OSHA. We have all the different things that will help us determine how safe things are. And usually we use ppm and ppb when we're talking about contaminants, because we're probably looking at very low quantities, but you can also use it to talk about salinity. Salinity is the amount of salt in something. Okay, and one important thing here is to realize that parts per billion times 1,000 will give you your parts per million. Okay, now you look at this mass solute divided by mass of solution times 10 to the 6th. And a good way to do this when you're putting this into your calculator is that this should be times 1 times 10 to the 6th and times 1 times 10 to the 9th. I think it's a little bit better to put it into your calculator like that. Okay, now let's figure out we're not always trying to solve for parts per million. You might be thinking, well, how do I turn these around? If you're given a parts per million and you want to find your mass of your solute, then you turn it around like this and you say the mass of your solute, and this will be important in the next slide, is equal to your parts per million times the mass of the solution that you're looking at, divided by 1 times 10 to the 6th. And then if you're dealing with parts per billion, then you can find the mass of your solute by taking your parts per billion times the mass of your solution divided by 1 times 10 to the 9th. And again, this is when it's in the division here, it's really important to make sure you're using that exponential expression on your calculator correctly. And if you're taking this with me in class, then you've actually had like 4 or 5 weeks already where I've been helping you use them. I just want to remind students at this point that if you are taking this with me online and you're consistently not getting the correct answer on your calculator, take a picture of your calculator and email me that picture and I'll be able to tell you exactly how to do that. And if that still doesn't work, send me a quick email and say, hey, can we Zoom? I can set up a Zoom within 24 hours with you. And you can share your screen and I can actually look at your calculator and tell you exactly how to work through that. So again, don't struggle with how to put scientific notation into your calculator. If you're not getting the right answer, schedule a Zoom meeting with me and we can set that up and I will teach you how to use it. I've never met a calculator I couldn't figure out. Okay, so one more slide, and then you guys will be free to start your own homework on this. Okay, according to the EPA, when the concentration of lead in tap water reaches 15 parts per billion, certain remedial actions must be taken. What is the concentration in parts per million? At this concentration, what mass of lead in micrograms would be contained in a typical glass of water, which is about 300 milliliters. And again, this is just sort of about, so we're rounding what's one significant figure in the end here. Okay, so first of all, you can see here where they have this thing here, they sneak in this question, what is this concentration in parts per million? And so if you have 15 parts per billion, you have 15,000 parts per million. So it's always important to think about what are we actually looking at here? 15 parts per billion sounds really small. 15,000 parts per million seems really big. So let's kind of take a look at what that would be. Okay, so now our step one here is to use the parts per billion equation to determine the mass of lead, which is our solute, in grams. So what we're working with now, let's take a look at that. Okay, so we're going to use those equations that I had done before, where the mass of our solute equals. So what I had shown you on the previous slide. And so you're going to say, well, you have 15 parts per billion times 300 grams. Okay, and again, we're assuming here that we have 1 gram in 1 milliliter, and that's your density of water, divided by 1 times 10 to the 9th. Okay, now what I want you to do here is I want you to work this with me to make sure that your calculator is helping you get the correct answer. So 15 times 300 divided by 1 times 10 to the 9th. And what you should get out of this is 4.5 times 10 to the negative 6, and that's in grams. Okay, if you're not getting that answer, that's a great idea to give me a quick email and say, hey, can we Zoom? My calculator's not giving me the right answer. Don't wait until after the test to do that, because then I can't help you as much. Okay, and now because it's asking us for the mass in micrograms, because this is really small, it's hard for us to concentrate on that. So a lot of times when we're talking about parts per million or parts per billion, we're going to be talking about micrograms or milligrams, not grams, because they're just too small. Okay, so to go from grams to micrograms, remember that there are 1 times 10 to the 6th micrograms in 1 gram. That's from chapter 1. And so if we have 4.5 times 10 to the negative 6th grams times 1 gram goes on the bottom to cancel those out, 1 times 10 to the 6th micrograms. Okay. And we get 4.5 micrograms. Okay. And I stuck with the 2 significant figures because of that 15 parts per billion had 2 significant figures. All right, that is the end of chapter 3. The rest of this are these slides here. These are our in-class homework problems. And so if you're meeting with me in class, that you will be doing these here. Okay. If you're not meeting with me in class, then these are your online homework. Okay. And what I want you to do is I want you to go through these, show your work. And at about a day before the test, I will send out an answer key for them. And then you'll be able to check your answers. If you want the answer key earlier, send me an email and I will send you the answer. Just send me an email and I will send it to you. There's just other slides here, and you'll see that in some of these, I give you just the problem. And in some of them, I will walk you through the steps as well as giving you the slides for what you should be looking at for them. Okay. Okay. Wow, that was chapter 3. I look forward to seeing you either on Zoom or in class.